Now let's solve the equation 3x squared minus 5x equals x times the quantity x minus 5 plus 24. To solve this equation, we're going to go ahead and think about what it is. Well, it's got an x squared term, so it looks to be quadratic. Let's go ahead and concentrate on trying to get 0 on one side since it is a quadratic equation. So first off, I do need to simplify a little bit. I do have a distribution there. So 3x squared minus 5x, and then doing the distribution on the right, I have x times x, which is x squared, and then x times 5 is minus 5x. And then we still have that 24 there. So now we can see two x squared terms. Let's move those x squared terms to one side. If I move this x squared over, 3x squared minus x squared is 2x squared. Minus 5x equals negative 5x plus 24. Let's continue to get 0 on one side. So if I do that, moving the 5x over next, negative 5x when I move it over will be positive 5x. Negative 5x plus 5x is actually 0. So these two 5x terms actually go away when we actually add them together on the same side. So we actually get 2x squared equals 24. Now I could continue to get 0 on one side, but this is one of those special cases with quadratics. If the x term goes away and we're left with an x squared term and a constant term, you can actually simplify the process and instead use the square root method by isolating the x squared and then square rooting to get the x by itself. And so let's do that here as an example where we have this special case where the x terms went away. All right, so to use the square root method, I do need to isolate the x squared. So divide out the 2. So x squared equals 24 divided by 2 is 12. Then you can use the square root method by undoing the square with it. So x is equal to the square root of 12. The thing you have to remember is that when you do this, technically a square eliminates a positive and a negative, and so you have to bring them back. All right? So when we squared x originally, it could have been a negative, it could have been a positive. Either way, you get a positive 12. So when we undo the square, we have to bring back both the positive and the negative. Remember, when you use the quadratic formula, you get a plus or minus. So when you use the square root method, you should get a plus or minus. So these appear to be our solutions, plus or minus the square root of 12. We could simplify that square root of 12 because it does have a perfect square of 4 in it. So if I write this as the square root of 4 times 3, the square root of 4 is actually just 2. Now that 2 is still attached to the square root in that it multiplies it. So it's 2 times the square root of 3. So if you're calculating this in your calculator, and in fact it's good practice to do that, you would have 2 times the square root of 3, and 2 times the square root of 3 is approximately 3.46. So we have plus or minus 3.46 there. If we wanted the exact values, it would be these two values, but we should check them. And remember, it is easier to check with the approximates. So let's go ahead and check with the approximate values. We have to go back to the original equation to check. 3 times 3.46 squared minus 5 times 3.46. Is that equal to 3.46 times 3.46 minus 5 plus 24? So since we're already approximating, use your calculator to go ahead and calculate each side out. When we calculate the left-hand side, I get 18.46. Whoops, no 4. I wrote that down wrong for my calculator. 18.6148, and on the right hand side I get 18.6716. Those are pretty close. They both start with 18.6 and then they change at the second decimal place, but remember we rounded at the second decimal place, so that's pretty good. That's really just can be attributed to round off error, so that looks good. You should always check the other solution as well, negative 3.46. Quantity squared, we're going to square that and then multiply by 3, and then minus 5 times negative 3.46. Is that equal to negative 3.46 times the quantity, negative 3.46 minus 5, and then plus 24. Calculate both sides. I get 53.2148 On the left side, I get 53.216 on the right side. Notice 53.2 in both of them. It only becomes different at the second decimal place, and that's because we rounded at the second decimal place. So round off error is attributing to why those are a little bit different. So those two solutions do work out. So I could go ahead and write up my solution set. The solution set for this problem is, and then again, we do list them separately, not with the plus or minus. So we would say -2 square root 3, comma 2 square root 3. I don't need the plus there because it's implied. Little reminder, quadratics will never have extraneous solutions. So if something doesn't check, you've got an error somewhere. The last of our 6 equations is a radical equation. X equals the square root of x plus 8 plus 6. So we've got a square root equation. So what we want to do is isolate the square root to begin with, because we can't get rid of the square root very easily until we have it isolated. So let's go ahead and move the 4 to the other side. So I'm going to get x minus 4 equals the square root of x plus 8. Next, we'll square both sides. So we're going to have x minus 4 quantity squared equals the square root of x plus 8 squared. Now the square undoes the square root, so I'm just going to get x plus 8. Over here, it's tempting to just square the x and square the 4, but technically this is the entire binomial squared, which means that it's multiplied by itself. And if you actually multiply it by itself, FOIL it out, you will get the x squared, but you'll also get some middle terms. You'll get minus 4x and another minus 4x from the FOIL, and then -4 times -4 is positive 16. So be really careful when you multiply or square a binomial, because sometimes we get in a hurry and we think it's just x squared and 16 when actually we have these two middle terms as well. So collecting like terms, we have x squared minus 8x plus 16 equals x plus 8. I've got a quadratic, so I'm going to move everything to one side so I get 0 on the other. So I'm going to have x squared minus 8x minus the x I move would be minus 9x. And then 16 minus the 8 would be positive 8. Now that's equal to 0. To solve a quadratic, we generally want 0 on one side. We have that 0 on one side. Now we can try to factor, or we can use the quadratic formula. I always recommend trying to factor for about 30 seconds just in case, because factoring will get you to the answer sooner. In this case, it will factor because 8 as a positive 8, you can think of -1 and -8 that add up to -9. So x minus 8 times x minus 1, double checking that adds that when you multiply that, you will get a -9x and a positive 8. Just always watch your signs. And then using the zero product principle, one of these two factors has to be equal to 0. So we can say x minus 8 equals 0, so x equals 8, or x minus 1 equals 0, so x equals 1. We should check these results. Radical equations can have solutions when you're solving the process that come up that don't actually work, that are extraneous, so it's important that we check them both. Starting with the 8, we get 8 equals the square root of x plus 8. Whoops, I got to put that 8 in. Remember, 8 is the value for x in my check here. So I'm going to have 8 plus 8 underneath the square root, and then the plus 4 is outside. Really watch that. Make sure that plus 4 doesn't end up on the inside. So checking the two sides, the left side is 8. The right side, the square root of 8 plus 8 is 16. Careful that you don't try to multiply that. Add the 4. Square root of 16 is 4. 4 plus 4 is 8. So we get the same thing on both sides. So this one looks good, x equals 8. Now let's check the 1. Remember, we are checking with the original equation. 1 equals the square root of 1 plus 8, and then plus 4 on the outside of the square root. So 1 obviously on the left side. On the right side, we have the square root of 1 plus 8 is 9. And then we have the 4 still. And then the square root of 9 is 3. Add the 4, we get 7. So here we have a false statement. Okay, so that 1 is not working. That's an extraneous solution, so we want to cross that one out because it doesn't work. Now, why doesn't it work? Well, you should be able to see why it doesn't work at a certain stage of the process. Remember that when you're working with absolute values and square roots cannot be negative. Okay, so let's take a look at the process here where we have the square root isolated. So we look at this step right here where the square root is by itself. And if we think about having a 1 minus 4, we actually have a negative 3 right here. And this is saying the square root is equal to a negative 3. Now, the square eventually eliminates that negative, so it seems like everything's okay as we go through the solving process. But at this stage, and this is why you always want to check back to the original equation, what we have is something that is not true mathematically. A square root symbol, when you're calculating with a square root symbol, you have to get a positive number or 0 out. You can't get a negative, which is what this 1 is giving us. 1 minus 4 is negative 3. And so what we have here is an extraneous solution because the range of a square root function has to be positive. Same thing with an absolute function. When you find extraneous solutions, though, with rational equations, it's usually a domain issue. The denominator can't be 0. Okay, so extraneous solutions often come up where you have range issues, so like an absolute value or a square root can't be equal to a negative, or when you have domain issues where you have a denominator that can't be equal to 0. Either way, in this case, what we found is that only one of our 2 solutions checked that we found, so we would respond that that is the solution. So the solution set here is 8.